Sir?
Yeah.
Yeah, yes, sir.
Yeah. Hello, everyone. Welcome to the first lab of Design Compiler. Since this is the first lab, I'll be focusing on the very basics of Design Compiler. And I'll invoke Design Compiler. I'll tell you how to get help in the Design Compiler, how to get help on commands and variables. We will look at the library setup in detail. We'll take a look at the what is inside the library, how to report the information in the library, and so on. I have a design example which has multiple RTL files in Verilog. It also contains a memory, so that will be very helpful for understanding how to handle these kind of macros. So let's start with the very basics. So this is the structure. This is the structure in which we should arrange our files. This is the recommended structure. Obviously, you can follow your structure also, but it should have some logical basis to it. This structure is something like this. In the RTL directory, you have all the RTL files. So there is a README which tells what are the changes. So this is again this example design is from Synopsys. So we use this in our lab. Then the folder models contains the library. We'll look into all these libraries in detail. Then there is scripts which contains the DC script for your design, which you would use for synthesis. Then work is the folder in which you would start invoking DC shell and do a lot of work. Then output is the one in which we would store the output from the design compiler. So what is the output for the design compiler? It's the netlist. The most logical output from design compiler is netlist. You could always also write out the constraint files, whatever you apply. So we would redirect all the outputs to this directory. There is one more folder input which has the one more SDC. So for now, I would for this session I would not source any script file. I would actually write out each and every command so that it's very clear how do we go about doing that. So let's go to work. I'll just clean up some of these stuff just to start afresh. So now in this session, the design compiler is already set up. So you could see what DC shell points to. DC shell points to the place where Synopsys design compiler suite is installed. So the command is DC shell. I'll just invoke it. Now whatever we enter into DC shell, we can actually redirect to a log by using the T command. So now whatever we type inside DC shell, the log will be stored in DC.log. DC by default also writes out command.log, but it's not that easy to read. So you should always make sure to redirect. The command.log contains the log plus a lot of extra things. So to get a simpler log out of DC shell, this is the best way. Now when DC starts, it will usually list down the various licenses and various features. So these are various licenses and various feature names. So what we would be using is either DC Ultra and DC Expert. So the compile command belongs to the feature DC Expert. Compile Ultra command belongs to the feature DC Ultra. SDL compiler is the one that reads in your Verilog files and analyzes them. Again, DFT compiler is used for scan. Designer is a suite of design some pre-made IPs from Synopsys like adders, multipliers, etc. Library compiler is the feature that will parse your library files. Power compiler, as the name suggests, will be used for power. Forget about BSD compiler for now, and program manager. You need to worry about those. So it looks like Compile Ultra license is enabled. So we would be using Compile Ultra. If you have Compile Ultra, please use it. If you don't, then use Compile. So Compile Ultra is a much more advanced and evolved form of Compile. So I would recommend using it whenever it's available. This is the version. So if you're working for trial synthesis for your labs and all, you don't need to worry about the version. When you work in an industry, you should be very sure which version you will be using, because some of the versions will contain some bugs. Synopsys might fix them, so we should be very clear about what version to use, and make sure that all the designs of the chip are synthesized using the same version to avoid any pitfalls. Now, in DC shell, this is the tickle command mode. I am not going for GUI mode. You are always free to experiment with it, but I find text-based interface a lot more powerful than GUI mode. The reporting is a lot more intuitive here. So I would focus on the text-based interface, as it's very popular in the industry. But please feel free to explore the GUI mode. It's for design written. Whatever, I mean, I can only say that you're not missing anything by going with GUI, by not going with GUI mode. So all the features are contained inside the text-based mode. GUI is just it will just show you some block diagrams of some circuits, which will be useful in some very simple cases. Otherwise, the text-based interface is quite sufficient. So when you type help here, you would get a list of all the commands. So this is a list of commands that is available to you inside this shell. So now, if you, let's say, want to see what are the commands that can work on libraries, you could do something like this. So this will tell you the list of commands that contains the letter lib. So I would, let's say, I want to know what are the reporting commands. So I can say report star. It tells me these are the reporting commands available to me. So as you see, there are a lot of commands. We'll go over the most popular ones, and always for anything you want to do, set it over the documentation. Now, each command has two types of help available. So let's say I use a command called let me choose a simpler command called, let's say, define design list. Now, define design list, so the tab works very well, so it will auto complete the command for you. So define design list should do a minus help on the command. So minus help tells us that what are the options available. So what it means is that define design list, a small summary. It is SDL define design list. The option available is minus path and minus path directory. So this tells us that these options are available. The library name is the logical name, and minus path will be pointed to a specific directory path on your in your directory. So you could, for an extensive help, you could do something like this. You can say man is a manual, short form of manual. Man define design list. Now this is a much more descriptive help on a particular command. So what it tells us is that this define design list command maps a design library to a Unix directory. So design library is a logical name, Unix directory is a physical path. So every command is a return status. So this is the syntax. It tells us what the arguments are and it gives a description. It also lists down some examples and it tells you what all commands are related to this command. So it is clear from this command define design list that it is related to analyze and elaborate. Now let's look at the libraries first. So we'll go out of this. Okay, now let's see the libraries first. So libraries are stored into the directory models. Let's see what is there. Now there are two. Let's first focus on the standard cell library. So this is the standard cell library. SAED. This is from Synopsys, and now it has. If you notice that it has three .lib files and three .db files. So the .lib file is a text readable format. Each of these corresponds to one particular operating condition. So FF1C16 V and mine 40 means this belongs to a fast corner. Fast means fast PMOS, fast NMOS. 1.16 volts is the voltage, minus 40 C, N is for negative, minus 40 C is temperature. So this is a fast corner or the best case corner. This is the slow corner. SS means slow, 0.95 volt. So again you see that there are two extremes here, lowest voltage to highest voltage. This is a typical corner. So the typical corner will be the operating voltage and operating temperature at which our chip is supposed to operate, and the other design corners are the margins for which we should make sure that our design will work. So typically the voltage is 1.05. It can go, so the range of the chip for which we are which we will qualify the chip will be from 1.16 to 0.95 volt. So what is the worst corner? Worst corner is when the devices are slow, that means NMOS and PMOS is slow. SS when the voltage is lower, mostly in most of the cases it will be minus 10% of VDD. VDD here is 1.05 volt. So there is some margin. So 0.95 is the lower side. The devices will be slower, and high temperature. Temperature is 125. Here the typical temperature is 25. Right. So TT means typical. So these are three corners. One is this is the best case corner. This is the worst case corner. This is the typical corner. As I stressed a lot of times before that synthesis has to be done at the worst case corner, at this corner. If you compare any cell, so both these libraries will be exactly same in terms of the number of cells, the cell functionality and all that. The only thing that changes is the timing numbers and the power numbers. So you could actually see, compare both of these libraries, pick up one cell each, and you would notice that the slow corner has more delays than the fast corner. We will see, so synthesis will use the slow corner, the worst case corner, and we will see what is the use of the fast corner and the typical corner. We will see later. It will come in unit 5. Right, but for this lab, we will keep using the worst case corner, that is the slow corner. The .dbs are written from DC shell again. These are the binary versions. So design compiler, can read .lib, but it is preferable to give it a .db. The processing becomes much more faster. That is why we prepare these lib files. We read in and write out the db files before even starting synthesis. This is a very simple command called write lib. You could read lib and write lib. That will do the job for you. So I have already written out the DB so that we can use directly. There is one more file, there is one more library which is for the memory. So you have a lib and a DB, very similar to the standard cell. Now let's see what is inside the list. We have seen some examples in the lecture slide, but let's look at it. It will be much more intuitive now. So this is the library name. This is the library name. The first few lines tell the set some define some variables. Important here is technology CMOS delay model stable lookup. What is stable lookup? Stable lookup is non-linear delay model. So non-linear CMOS delay model is represented by a stable lookup string. It also has the time units. Leakage power unit. The library defines all the units. Then it will define some threshold values. So these are the threshold values used for calculating rise time, fall time, 2080. So we know from here that the limits for calculating the transition times and the rise and fall delay are from 0.2 VDD to 0.8 VDD. Similarly, these threshold here, PCT means percentage. These threshold here define that how do we calculate delay from input to output. The delay is calculated by taking the 50% of VDD of output minus 50% of VDD of input. So these thresholds define that. There will be some default pin caps, some default loads, and so on. I will not go through everything. This defines the nominal voltage. So the worst case library has a voltage of 0.95, temperature of 125, process 0.99. This thing does not matter for this because there is a separate library for each. There will be some wire load defaults. So now this part defines the wire load. There is also something called voltage map that will fit some voltages. So VDD is set to 0.95 here. VFS, which is ground, is set to 0. So these are the wire load models. These are different wire load models that are available in this library. Also, there would be a wire load selection. There's a wire load selection group which tells us that how the wire load is selected. So this is automatic area-based wire load selection. So wire load from area.
99 full day selection.
So this is the wire load selection area, and so now this is the place where operating condition is defined. Process, voltage, temperature, and retype. And now comes the lookup table, the lookup templates. Now let's see one cell. So this is a cell and 2x1. So this is a cell. The area is given. The leakage power is given. Let's not focus on the PG pins for a while. That will come later. This is I can only tell you that this PG pin is used for low power synthesis flow, and this is outside the purview of this course. So this is used in the low power pin. Now what it defines here is the pin. So pin is defined. Direction is input. There are capacitances available. There are some power numbers here. Similarly, A2 is again a second input pin. It tells what is the fan out load. If you remember that how the fan out calculation is done, it tells the fan out load, and then there's a pin called Y, which is the output pin, direction output, and function. This is important. This tells what kind of gate it is. It is an AND gate because it's A2 and A1. Now, so there are power numbers and there is the timing number. So this is the lookup table. So this is the cell rise tells us that with respect to pin A1, when A1 changes, timing sense is positive unit means when A1 will rise, output will rise. When A1 will fall, output will fall. This is called positive unit. Negative unit means when input rises and output falls. If there is an inverse relationship, it's called negative unit. So this cell rise, there are two indexes here. It uses this table. So we can see what this table is. You can look at the top. So this is the lookup table it's using. Variable 1 is input net transition, variable 2 is output cap, and if you see index 1 and index 2 values, they are both same values, but they are dummy values. So whenever this table is used, the indexes are assigned the proper values. So this is transition value, these are capacitance values, and the values this table will tell what is the delay. So for example, this is the delay part when the transition is this and the cap is this. This is the way you can understand this lookup table, how it is arranged. So there are different cells. There are a lot of cells here. For each the important thing to know is how to see the area numbers, how to see the function. So DC will use the function to map the design. It will use the timing and area parameters to optimize the design. It will use the power number to do some power calculation and power optimization, but we'll see that later. But let's focus on area and timing for this these few lab sessions. Right? So these are, let's look at one of the sequential cells. Let's look at a scan plot. So this is a plot SDFF. Now the function here is represented slightly differently, as we saw in the slide. It's represented by FF IQ IQN. It's clocked on CLK. The next state is this. So next state depends on the pin called scan enable. So if the scan enable is low, the D will represent, the data pin is represented by D. If the scan enable is high, the data pin is scan input. Let's look at the non-scan. It will be simpler to understand. So non-scan flip-flops are usually DFF, represented by the name DFF. Scan ones are called SDFF. This is a very global kind of naming convention. So here it is clocked on CLK. Next state is D. Clear is represented by RSTB. And here the pins are listed. Go down. This is the pin D. So now D. Now an input pin of a combination element does not have any timing parameters. It just has the fan out load. That's it, and some capacitance. However, a D pin will have the timing parameters which are nothing but setup and hold. So this is the setup, and this is the hold. So this is the setup when D is rising, when D is falling, related pin to CLP. Right. So the setup rising tells us that the timing is with respect to the clock rising. So this is a positive edge triggered flip flop. So these timings are setup rising, hold rising. You could go through it at your own pace and see that. Don't worry about the negative values. It's not. It's very common to have negative hold values. You could read about it online why the hold values are negative sometimes, but it's common to have that. Now let's go to the pin Q. So this is a pin CLK. Now DC knows from this clock through that this is a clock pin of a flip flop. Again, clock does not have any timing parameters. It just has power parameters. There's a reset B pin. Now reset B. Now a reset B which is asynchronous will have a recovery removal timing similar to setup and hold. Recovery and removal. This is the reset pin, and then we go to the output pin where the function is IQ, which is again we saw at the top that how the function is represented for this, and then it will have the timing numbers. Timing numbers are with respect to the clock, rising edge. So cell rise. Output will have now two things. One is the delay part, other is the transition part. This is the NLDM model, and so this is the delay part, and this is the transition part. Cell rise, rise transition, cell call transition. Right? And then there's a timing with respect to the reset pin. So now what does a library have? Let's summarize. Library has a list of cells. For each cell, the function is defined, the input output pins are defined, timing is defined. The output pins will have the delay and transition numbers, timing numbers. The input pins for combination will have nothing, no timing numbers. For sequential, they will have setup hold timing. Right. Now let's go to DC again. And go to DC again. Now how do we start? The first thing we do, we know where our libraries are. We need to specify. We need to tell DC how does DC point to the libraries. So the first thing, now I talked about commands. There are two things. There are a lot of things called variables. There are a lot of variables which control the functionality of design compiler. How do you get a list of variables? You just say a print var. So this is the list of variables and the default values we see. For example, we could see what is the search path. So this is the search path. This is the default search path. The search path points to the current directory and some directories inside tool synopsis. So the first thing what I like to do is set the search path. I usually set the search path to where my RTL is and to where the libraries are. Now what I did here is I set the search path to, I appended some things to it. I appended current directory in which already present. I appended models and the RTL. This is the first thing I did. I set the search path. I'll tell you how it is useful. Now, since I've included models and RTL, if I read the RTL file now, I don't have to give the complete path. Since this is included inside search path, so DC will search for it inside the directories listed in the search path and it will automatically find it. Second thing I do is that I set the link library. Now this link library is we set the link library to star. Star means already loaded memory designs in memory. This is you can read about link library by reading the man page, but this means that link library is the list of libraries that will be used to link the design at all points of time. That means even before synthesis, after synthesis, always. So link libraries should have a list of all the libraries and all the designs in the memory. The star represents the designs in the memory. This tells us what are the other libraries available. So what we have available is the worst case library for standard cells and some library for memory. Here I do not have a worst case library for memory, so I am using the typical. It is okay to have this for trials, but whenever you are working on real projects, please make sure that all the cells, memory, standard cells, all analog macros, should have the worst case library available for synthesis. Now I set the link library. To know what is the link library set to, I can do an echo $link library, or I could even do a print var on this. So this tells me that link library is set to this. Then what I do is next I set the target library. Now target library is a set of libraries which can be used by DC to map your design. Please, it's very important to understand the difference between target and link. Link is a superset. It contains all the libraries. Target contains only those libraries that DC should use for mapping. Now what does DC use for mapping? It uses the standard cell libraries. It does not use memory libraries for mapping. A memory is a hand instantiated cell. That means if you want to use a memory, you should instantiate it in your design. You should use it directly in your design. There is no way DC can map a complex logic to memory. That is why a target library should contain mostly the standard cell library. Right? Now we have set all the libraries. Now what we could do is okay. Now till this point only the libraries are set. The libraries are not ready yet. When the libraries will be ready, when we read in the design. So till now it's only DC is only preparing stuff for you. You have only set the library some variables, but nothing has happened yet. No reading has been done. Now we define some design lib path, the command we were saying earlier. So I defined a design lib which tells DC that in the current directory, in the physical directory work, is your work directory. Now every time DC reads an RTL file, it will create some intermediate files. Those will go into this. Now as soon as we do this, we see that when we read in the first library RTL file, we'll see what happens. Now let's read the first RTL file. So I am reading just a part of this one file from the complete design. I am not reading the complete design. We'll start slowly. We'll build this up. We'll read the complete design later. Now what I do is I just read in one RTL file. This is the command analyze minus format verilog. So you could either use analyze elaborate or read file. I am using analyze elaborate. It's much more intuitive. So analyze minus format verilog, and I tell minus library work. Now here I map the library work to the physical directory, which is also called work, and I read in this file. Now please note I haven't given the full path for instruction decoder. Now as soon as I give this, DC will launch the presto compiler, which is the feature that it is searching for instruction decoder in the list of directories given in the search path. It found it. The compilation is completed. So this is only a syntax check. Now at this point, DC loads the library. It reads the libraries given in the link path. Now I can do some commands. I can use some commands to see what the libraries are loaded. Let's do some reporting now. We'll elaborate this first and see what happens. Now assuming that this instruction decoder is my top level design, I will elaborate it. You typically will only like to elaborate from the top. So let's say you read in 10 RTL files, you will give in the elaborate, you will give the design name, the module name of the topmost block. Here since it's only one RTL file, I'll just give the name of the. So I'll open this. I'll show you what the RTL is. This is the RTL. This is the module. This is some kind of instruction decoder. The comments on the top also tell what does this block do. This is some instruction decoder. It has a clock. It has a reset. It has some inputs, some outputs. It is simply it has some instruction bus, and it will give out the enable signals. This is an instruction decoder for a mini CPU kind of logic. So this is the RTL here. I see that there is one always block. There will be a list of registers here, and so the module name is called instruction decoder. So I'll just give the elaborate command. Now what happens? Now the analyze command, it just takes the syntax of the RTL file. It did not do anything else. Elaborate command will now run a lot of rules here. It will now try and map the design to the GTEC components. That's what elaborate does. Please go back and read about elaborate. That's what elaborate will try to do. It will try and map your RTL design the GTEC components to the technology independent library that Synopsys has. So it will do all kind of inferences. What it tells us that there was an always block. It tells us that it is inferred memory devices in process. In routine instruction decoder line, it gives the line number in this file. Routine is the module name, file name is given, and now it tells us that it found so many registers. So we saw one always block. It is reporting with respect to that. The width, it tells us the width of the registers. It tells whether it's bus or not. If width is more than one, the bus is yes. Otherwise, it's no. It tells us whether it has asynchronous reset, asynchronous set reset, or synchronous set or synchronous reset. Now let's go back and look at the RTL again. Now it will append _reg to each one of the names. So let's look at the instruction. Let's look at this. in stretch is a register. There are some wires which work on this based on the value. Then it is assigned to some wires, and then the register itself is this. So we see this that there's a this always block. We see that it has a synchronous reset. Why? Because it is not in sensitivity list. If you notice, then the if command is the first one. If what happens on reset. So there's a pragma also, synopsis sync set reset reset. You could try removing this and see what happens. Usually it should work fine because the coding style is good. So DC should make the synchronous reset clock, synchronous reset clock, and then there's some functionality on. So now, so for each of the registers that you work on, it is good to see for each of the RTL file. It is good to see the elaboration report at least for the first time. It gives you a lot of. So if your register is not appearing here, there's something wrong. Maybe it appears as a latch which you did not intend to do it. Maybe you targeted it to be a flip flop, but it became a combination logic because of coding mistake. So a lot of info is in the elaborate file. Now at this point, the design is master G-Tech. Is it possible to see? Yes, it is possible. What we could do, we could use a write command. You can say write -f format. You can say Verilog and minus output. Let's say IIT G-Tech dot B. So it wrote something. Let's see what it wrote. So this write command is the one that is used to write out the network. Now please remember that the synthesis has not been done. We haven't issued any compiler command. Now let's see this. What kind of netlist that we get. What we get here is a G-Tech netlist. So we looked at the sequence gen block. This is the generate sequential element. So you could see that you could compare it with the block diagram given in the lecture slides. So and then there will be a host of, so there are a lot of flops. At first all the flops are listed, all the segments are listed, and then there are some G-Tech components, G-Tech not, G-Tech or, and so on. Right. So this is the G-Tech netlist. How is it used? Is G-Tech netlist useful? There is no optimization that has taken place as of now because there is no synthesis that has been done. The use of G-Tech netlist is that, let's say you want to deliver your code to some third party and you do not want them to see your RTL, your design. You could always give them a G-Tech netlist. And if they are using the same tool, Synopsys Design Compiler, they can use this to plug it in their design. They can use your code in the G-Tech form and use it in the design. Use it for synthesis. So this way your code is protected. They cannot read it, and they can also go ahead and synthesize it. So this is one of the uses of G-Tech. Now let's look. Now I won't go into compile into this in this lecture. We will focus on the compile command in the next lecture on the constraints, etc. Let's focus on some of the reporting. So till now we see that how do we set the libraries using link path target using these commands. Link search path, link library, target library, define. Now let's see that what effect this design has. So it created a directory called work. Inside work, what is there? Inside work there are few binary files which belong. So we read a module called instruction decoder. So these are the intermediate files that Synopsys generates, design compiler generates for us. It is not used by us, but it is used entirely by the tool. Do not worry about that, but it is a good practice to create a work directory and link it to the logical directory work whenever you are working. Otherwise, what you do is you dump a lot of files in the present working directory, which you do not want. You want this particular area to contain your log files only. So it's a good thing to create a separate directory and point design compiler to that one for writing out these intermediate files. Now, so we saw how to set these link library, target library. We saw define design list. We saw how to read a single RTL file, and what does elaborate command tell us. Right. Now I'll show you a couple of reporting commands that are very useful for library. So first command is list_library, list_libs. That tells us we see that what are the options there available to us. This nothing. It's you can either want a particular library to be listed, or you can. So if you issue this command, it will give you all the libraries that are loaded. What is loaded? Library name is this. This is the file, and this is the path. So standard cell is loaded, memory is loaded, GTEC is loaded. GTEC is part of the tool. It is not something that any technology library will provide you. This is included in the design compiler tool. And standard SNDB. Standard SNDB is a list of symbols that are used to show you the block diagram when you use the GUI mode. Right. Now there's one more command called report underscore. Now this tells us what is the library, what all libraries are loaded. Now we can do a reporting. So lists will give you a list of things. Report commands can be used to report on those things. So I want a report on the library, on the semester library. So let's look at the options we have. There are so many options available here. So what does the library contain? It contains cells, functions, timing, power, noise, data, a lot of data. It contains a lot of data. This report command. So one thing is you can either open up in a text editor and see it, or design compiler also gives you a summary report. So what I'll do is I'll just do a square brace here. There is that these options are optional. You could and this is library name is without this square brace. So that means this argument is compulsory. So I'll just give one argument. I'll just say report underscore lib. And I'll report on this library. What does it give me? It gives me that it's a technology library and it has power ground pins. It is created by this tool. It is created on this date, whatever. Library version, time unit. It gives us all the unit information. It gives the operating conditions. Forget about input output voltage for now. It tells us what is the voltage value, some default values. Whatever we saw in the library, it's all here in this report, and it's easier to read a bit compared to the text file. It gives a list of wire load models. It also tells that for a particular length, for a particular fan out, what is the length it will use for a particular wire load model. So it gives a list of wire load models. So these are all the wire load models. It tells us also about the wire load model selection group and so on. Then it tells us there was hardly any text, and the variable names, there was no comment on it. Here DC will also tell you the comment. So what does this mean? Delayed threshold trip points. So input threshold percentage rise, output threshold percentage rise, and so on. I've already explained this. Now it also gives a list. It gives some legends that now it starts listing the components, that is the cells, and before listing the components, before listing the cells, it tells what kind of cell it is. It's either a black box or a test cell or a scan cell. So there are a lot of legends. It has level shifter, map only. So now DC, it needs to know, apart from knowing whether it's a combination cell or a sequential cell, apart from knowing all the stuff, it also needs to know some other stuff. This collection of stuff is called attributes. Each particular cell has some attributes associated with it. For example, let's look at few examples here. Now, for example, take a simple AND cell. Now, it doesn't have any attributes. It's a simple combination cell. But look at an antenna cell. This antenna cell is a B. That means it's a black box. The legend tells us that B means it's a black box. D means it's a don't touch. And U means it's a don't use. What does these three mean? This means that antenna is some kind of special cell. The black box means DC does not know the functionality of it. Why? Because there is no function attribute defined. You could go back to the library, you can open the text file, list file, and see for yourself what is an antenna. There will not be any function attribute. Now, antenna cells are typically they are very special cells which don't have any functionality, but which are used to correct some problems in the layout. Now, a standard cell library contains all kinds of cells. It contains all the combinations, sequential, special cells, such like antenna. But antenna should it be used in synthesis? No. It is a cell that might be used by the layout engineer to resolve some problems, which are very specific to layout. It has no functionality, but it still is a part of the standard cell library because the same library is used by all. It is used by the synthesis guy, it is used by the timing analysis guy, it is used by the backend team. So the library is common, and these attributes are a way to tell the tool that this cell should be used or not used. So just because first thing it's set to black box, second thing it's set to U, which means don't use. U means that do not ever use this cell, do not ever insert this cell. So DC will not use this cell to do anything. So even if, let's say, function was defined, then it would not have been a black box. But if you set a don't touch, sorry, if you set a don't use, then DC will not insert that cell at all. Don't touch means that if this cell is already present in the design, so this cell could be present in the backend in the post layout, right? Because the layout engineer might have used it. If this is present, then don't touch it. Many people, they like to instantiate some technology dependent cells in their RTM. We will see the examples in this design also, and they want DC not to remove them. They want to tell DC that I have placed this cell, and please do not touch it, do not remove it. So that is represented by don't touch. Don't touch tells DC that do not play around, do not modify anything related to this cell. Don't use cells, do not ever use this cell. So now there are, for example, there is a cell called AO_X1, right? The functionality is known, it's not free, but we are telling that do not touch it, do not use it. What does AO mean? AO means it's an always on cell. It's an always on cell. Fine, always on is an attribute used for power analysis, but so for each cell there are some attributes defined, right? So here, for example, ISO cell tells us it's an isolation cell. So all special cells which have some special functionality, which might be used for voltage domain processing, might be used for solving DRC problems in layout. All these cells should be don't use and don't touch in the library. If the cell is not, if let's say the library guy missed something, you could always give commands in DC to accomplish that. But usually it's a good practice that it comes from the library. So S, I guess, means sequential cell because all the latches are attributed as S. So there are, so this is a S, this is a retention kind of a cell. So there are a lot of special kind of cells. This cell, this is a scan cell, scan type of a cell, and so on. So report lib will give you everything. I think there is also a summary. Is there a summary also? No. So let's see what all. Now report list did not give any timing information. By default, it will just throw out list of load models, the variable settings, and the list of cells and the attributes. You could also see the timing data. It will be a big report. You could see minus timing, for example. So it will also list out the timing data. So here it started dumping out the lookup tables, and to see it started dumping out the index and the value. So this is just again a different sort of a view for the library. So it's just dumping out the data from the .lib file. Right. So so report lib and list lib is a very useful commands to know more about libraries instead of going and opening them in a text editor. These reporting commands are much more useful. Now, so we read in the RTL, we read in one file. So DC will we elaborated that. So DC will set by default it will set the current design to be whatever design you elaborated. So by default current design is set to whatever we elaborated. Since we elaborated instruction decoder, DC set this to instruction decoder. Right. Now, if you want, you can just give a compile command simply and see what happens. Let's see. So what I'll do, I'll just give a compile command. I haven't defined anything. I haven't defined any timing constraint. I haven't defined any area constraint. I haven't defined any environment constraint. But still, let's see what happens if I give compile. Now, what it does is that compile ultra, since it's the first time we are running compile, it will load up the standard cell library and it will do some analysis. So it will say analyzing this, and so it takes some amount of time. The bigger the library is, the longer it takes. So what I'll do is so meanwhile it will I'll go over the command and see now we elaborated one RTL file. Now what happens? What if you want to read the complete design, whatever all the RTL files? So you could do it in this way. You could say analyze my primary work, format and then in the curly braces you can specify all the RTL files. This is a list of all the RTL files. The backslash is for escaping the new line, so that it's much more readable. And let's see if it's done. It will take some amount of time. So what I'll do is let's look at the compile commands in more detail in the next lecture. So for this lecture, please focus on. You could go back to your DC shell. You open up the DC shell. Play with these commands: search path, link library, target library. Read in, write a small sample RTL code using the lecture slides of RTL coding. You can try and write a small FSM, for example, or use the FSM code from the lecture slide and read that in design compiler. Look at the elaborate report. So the focus of this lab was to make you comfortable with library and the elaborate report. So please focus on the elaborate report. Read in different kind of RTL files. See what the elaborate report contains. I'll focus on the compile command of this design. We'll talk about the design constraints, the environment constraints, how to set them, and then how to synthesize the design. Thank you.